February 16, 1943. The small tool shook a little in Chief Engineer Klaus Hermann's hand as he opened the closed metal box of the American radio they had captured. 5 of Germany's top radio experts gathered around him, ready to check out the gear they got during the recent fight at Kasserine Pass. For 3 years, Berlin had told them that American technology was worse, just cheap junk built by a country of store owners and factory workers. The spy report said American troops used old equipment, simple designs, and people who weren't trained well enough. But things didn't add up. Their side kept talking all the time over very long stretches. Their ships never stopped talking to each other. Their army units worked together with an exactness that hinted at something much better than the basic radio's German news reports spoke about. Before we continue, show your support by subscribing and letting me know where you're watching from. The case opened to reveal an SCR-508 radio set, taken in perfect shape from an American M4 Sherman tank ruined in the Tunisian mountains. What Hermann and his team found over the next 3 days would wreck every guess German war leaders held about American factory power, technical skill, and the outcome of the war. The math of radio talk was about to show a truth more shocking than any loss on the battlefield. The careful look at the American gear would expose not just a technology gap, but a huge industrial difference, so wide that Germany's defeat was already set in stone by tiny frequency parts, automatic systems, and ways of building things in huge numbers that the country could never hope to equal. The capture started on February 14, 1943, in the Kasserine Pass. General Erwin Rommel's troops, in a desperate counterattack against inexperienced American soldiers, had won a small fight, pushing the U.S. Second Corps back 50 miles and wrecking over 100 American tanks. Among the destroyed vehicles, German technical spy teams moved fast, looking for weapons, papers, and equipment that might show what the other side could do. Hauptmann Friedrich Weber, who led a signal spy unit with the 21st Panzer Division, had standing orders to bring back any American radio gear whole. In a big hole east of the pass, his team found a left-behind Sherman tank. Its top had been blown off by a German 88mm gun, but its radio room was amazingly fine. Inside, Weber found not 1, but 2 complete radio sets, the SCR-508 made for tank-to-tank talking, and an SCR-510 listening device. Both were complete, with their tiny crystals, wires, and even the instruction book still fastened in their spots. Weber quickly ordered the gear moved to the closest German technical center, knowing this find could give them vital details about American communication abilities. The radios arrived at Technical Testing Station 12 on February 16th. The center, hidden in an underground building beneath Tunis, held Germany's best radio experts, men who had designed the German Army's own talking systems. Chief Engineer Klaus Hermann, a former main designer at Telefunken, led the checking team. With him were people who specialized in making frequencies, planning circuits, factory methods, and listening to enemy signals. They started by looking at the outside. The American radios were housed in thick steel boxes, painted dull green with rubber seals protecting every edge and plug. Hermann wrote in his first report that the build quality was better than anything he had seen in German military equipment. The boxes were built to handle water, dust, shaking, and high or low temperatures that would ruin most German radios. But the first surprise came when they opened the cases. Inside, everything was the same, built in blocks and designed for huge-scale building. Every part was exactly like the plans in the instruction books. There were no hand adjustments, no marks from technicians showing they had tuned it just so, no small changes that would need expert assembly. This was equipment made to be built by the millions, by regular workers in factories that could be spread across a whole continent. Lieutenant Hans Schreiber, an expert in frequency control, looked at the small crystal parts that set the radio's operating frequencies. He had thought he would find simple, cheap crystals, maybe even used civilian parts. Instead, he found precision quartz crystal oscillators, each one ground to incredibly tight standards, sealed in metal holders with requirements that would have taken weeks of lab work in Germany. The SCR-508 had 10 channels controlled by crystals. Each crystal was packed alone, could be swapped out with others, and was marked with the exact frequency. Schreiber counted the crystals twice, unable to believe what he was seeing. In Germany, radios controlled by crystals were only used by top command units and airplanes because of how costly and rare the precise crystals were. Here, in a regular American tank radio, 10 crystals were put in as easily as light bulbs. He carefully took out one crystal and looked at it under a magnifying glass. The quartz was perfect, the metal contacts lined up exactly, the frequency marked clearly. This single crystal would have cost more than the whole German Fu-G5 radio set in materials and labor. Yet, the Americans were putting 10 of them in every tank radio, and they had already made thousands of Sherman tanks. The team's first look showed even more worrying facts. The radio used frequency modulation, FM, instead of the amplitude modulation, AM, that German radios used. FM was better in theory, giving clear talk without static and blocking interference, but it needed much more complicated circuits and exact frequency control. German engineers had thought about FM for military use, but decided it was too costly and hard for field use. Yet, here was an FM radio, built in huge numbers, put into a tank, driven by young American soldiers. The circuit board showed automatic frequency control, AFC systems, that kept the radio locked onto the right frequency without constant manual turning. German radios required operators to keep turning the dials to fix issues caused by temperature changes, part wear, and power supply changes. American radios, it seemed, fixed themselves. Chief Engineer Hermann began writing his first report to the German Army High Command in Berlin. The words came slowly, each sentence going against years of news reports and spy guesses. He wrote that the captured American radio showed a level of factory skill that Germany couldn't match. The parts were made with an exactness that needed special factories, trained workers, and quality checking systems that just didn't exist in Germany. Even more worrying, the radio was clearly not a test model or a small batch model. Every part of its design shouted mass production. The Americans were building these radios by the thousands. Over the next 3 days, the team carefully tested every function of the captured radios. They hooked the gear to power supplies, antennas, and test machines that filled the underground lab. What they found with each test deepened their growing feeling of worry. The SCR-508's transmitter put out 25 watts of clean FM signal on any of 10 channels you could pick. The switch that chose channels was smart, reliable, and needed no technical skill to use. A tank leader simply turned a knob to pick a preset crystal, and the radio automatically switched frequencies, adjusted its circuits, and kept perfect transmission quality. In German radios, changing frequencies needed a trained operator to manually adjust many controls, replace coils, and spend several minutes getting the gear ready. Range tests proved even more troubling. Using a captured American whip antenna, the team made contact with a listening station 20 kilometers away. The FM signal came through clearly, without the static, fading, and interference that hurt German AM communications. Even when they purposely made electrical noise from a tank engine, the FM receiver's limiter circuits cut away the interference, giving clear sound that German operators could only wish for. Lieutenant Schreiber focused his check on the crystal system circuits. He traced every part, measured every power level, and wrote down the design in great detail. What he found proved his worst fears. The crystal control system was not just advanced, it was impossible to copy with German factory abilities. Each crystal part needed a exactly cut quartz plate ground to precise sizes measured in tiny fractions of a millimeter. The crystals were then placed in empty or gas-filled holders, with contact spacing controlled to standards that German factories could not meet in large-scale production. Temperature-fixing circuits kept the frequency stable even in temperatures from -40 to +60 degrees C. Schreiber figured that making one crystal to American standards would take about 40 hours of skilled worker time in German labs. The Americans had put 10 such crystals in one tank radio. With thousands of Sherman tanks already built, and similar radios in American Jeeps, trucks, and command cars, the Americans were making millions of precise crystals every year. He asked the plain question in his report: where were the Americans getting enough trained workers to make millions of precise radio crystals? The answer, when it came from spy sources, was even more upsetting. The Americans were not using highly trained workers. They had industrialized the whole process. New factories in places like Chicago, Newark, and Fort Wayne used thousands of regular workers, mostly women, running special grinding machines that made crystals automatically. Precise measurements were done by light machines and frequency counters, not skilled technicians. Quality checking was done by checking random groups, not every single piece. The Americans had changed a laboratory skill into a factory process. The look at the radio's receiver section showed even more advanced technology. The superheterodyne circuit design was like German receivers, but the parts were better in every way you could measure. Vacuum tubes were made to closer standards with qualities that perfectly matched the circuit needs. Capacitors and resistors were more stable than German parts could achieve. The whole receiver was designed to be adjusted by regular workers using simple test equipment instead of needing radio engineers with years of schooling. Most troubling was how it was built in modules. Every main part, transmitter, receiver, power supply, and control unit was a separate part that could be replaced. A tank crew could take out a broken unit and put in a new one in minutes without tools or technical knowledge. Broken parts would be sent back to repair centers or thrown away. This way of doing things needed massive factory power to make spare modules, but it meant American tanks kept talking under conditions that would leave German vehicles totally silent for days while technicians made field repairs. The team checked the instruction books that came with the radios. These papers, printed on nice paper with clear pictures and simple steps, assumed that operators had very little technical training. Operating steps were cut down to numbered lists. Fixing guides used simple decision charts that any soldier could follow. Maintenance directions spelled out exactly when to replace parts instead of trusting the operator's judgment. Herman realized that these books showed as much about American factory thinking as the radios themselves. The Americans had accepted that frontline soldiers were not technicians. Instead of training every radio operator to understand electronics, they had designed equipment that any reasonably smart soldier could run and keep working by following simple steps. This needed better equipment, but it solved the main Army problem of keeping communications open during fighting. German radios, in contrast, needed skilled operators who understood radio theory, could do repairs in the field, and had the technical sense to keep difficult equipment running. These operators needed months of schooling and years of practice. They were vital assets, and when they were killed or hurt, their equipment often became useless to whoever got it next. By the end of the third day, the examination team had written down every circuit, measured every part, and tested every function of the captured American radios. Their report to the German Army High Command was over 200 pages of technical deep dive, backed up by pictures, circuit drawings, and part lists. The findings were terrible. The Americans had radio technology that was 5 to 10 years ahead of German gear in key areas. FM, crystal control, automatic frequency systems, and modular building were huge benefits that couldn't be fixed by better battle plans or operator skill. More importantly, American radio equipment was planned from the start for mass production. Every part of the design showed a factory mindset that Germany simply didn't have. Herman's report guessed that Germany would need to build 30 new specialized factories, teach 50,000 extra workers, and spend money equal to the entire yearly Air Force budget to catch up with American radio production. Even then, Germany lacked the basic materials, especially high-quality quartz crystals and certain rare elements needed for precise parts. The final point was clear. American factory power had made technical superiority the main decider in the war. The report reached Berlin on February 25, 1943. It was marked Most Secret and given to only a few senior officers in the Army High Command and the Armaments Office. The response was silence. No new factories were approved, no urgent programs were started. The meaning was too devastating to admit. But Technical Testing Station 12's work was only starting. Over the next few months, more American equipment fell into German hands. Each capture provided new proof of American technical and factory superiority. An SCR-300 radio, the famous backpack walkie-talkie, showed FM technology shrunk into a portable unit that weighed only 18 lbs, yet gave clear talks up to 5 kilometers. German portable radios of similar range weighed over 40 pounds and needed extra battery packs that added another 20 pounds. An SCR-299 captured in Sicily in July 1943 amazed the examination team. This was a mobile long-distance communication center set up in a truck with a built-in power generator. The transmitter put out 350 W of power across a frequency range from 2 to 18 MGHz, with crystal control stability and the ability to change frequencies in minutes instead of hours. The SCR-299's partner receiver was a complex design with 15 vacuum tubes, many conversion steps, and a crystal filter for better signal picking. German long-range communication equipment of the same kind existed, but only in fixed places needing building-sized antennas and dedicated power setups. The Americans had packed the same power into a vehicle that could be driven anywhere and set up in an hour. Each examination showed the same pattern. American equipment was designed for use by minimally trained users, mass production by regular workers, and maintenance by following simple directions. German equipment needed skilled operators, hand assembly by trained experts, and field repairs by electronic specialists. One way scaled to millions of units and global use, the other did not. The spy reports flowing from Tunisia, Sicily, and later Italy wrote down not just single radio sets, but a complete communication philosophy. American forces kept talking constantly from small groups to whole theater commands through many layers of radio networks. Platoons had SCR-536 handy-talkies. Companies had SCR-300 backpack radios. Battalions had vehicle-mounted SCR-508 and 608 sets. Regiments had SCR-193 and 299 long-range equipment. Each level could talk to the levels above and below, creating a web of connections that German forces could not match. More importantly, all American radios used matching frequency systems and interoperable equipment. A spotter on the front line with an SCR-300 could call an artillery battalion 20 kilometers away, using an SCR-608 because both used FM on matching frequencies with crystal-controlled stability. German forces, in contrast, used many different radio systems, each needing different frequencies, different talk types, and different ways of operating. By summer 1943, German signals intelligence had documented over 50 different American military radio types, from small handheld units to airplane command sets. Production estimates based on captured serial numbers and spy reports suggested that American factories were making over 100,000 military radio sets every month. German production, including all services and types, reached about 15,000 units monthly at the highest point. The examination team started looking at captured American factory papers. Technical orders, parts lists, and maintenance manuals showed the system behind American equipment. Parts were the same across many radio types. Vacuum tubes used common base types. Crystals followed standard holder designs. Even screws, nuts, and bolts followed unified thread standards that allowed them to be swapped out. This uniformity meant that American factories could shift production between different radio types without changing tools. A plant making SCR 508 transmitters could switch to SCR 608 units by changing only a few small parts and component types. Parts from one radio type could often be saved to fix others. The whole system was designed for flexibility and scale. German manufacturing, in contrast, used custom parts for each equipment type. The Fu G5 tank radio shared almost no parts with the Fu G10 aircraft radio. Despite similar electrical jobs, each type needed its own production lines, unique test, equipment, and specialized spare parts storage. Changing production needs required months of retooling and retraining. Chief Engineer Hermann moved to a larger technical spy center in northern Italy by autumn 1943. He spent increasing time looking at American factory methods rather than just equipment design. His reports to Berlin changed from technical reviews of radio circuits to major warnings about factory capacity. He wrote down the American electronics industry's fast growth. Companies with names like Galvin Manufacturing, later called Motorola, had changed from small radio makers into huge military suppliers. Hallicrafters, a maker of amateur radio equipment, was building advanced military receivers in numbers that were more than total German radio production. Western Electric, the factory part of the Bell telephone system, ran plants using tens of thousands of workers making crystals, vacuum tubes, and complete radio sets. These companies had not been major military providers before 1941. The Americans had created an entire military electronics industry in less than 2 years by changing civilian factories, training new workers, and using mass production methods perfected in car and appliance manufacturing. Detroit's car engineers had designed radio production lines that worked with the efficiency of car assembly lines. The German radio industry, based in Berlin, Munich, and Hamburg, remained organized as it had been in the 1920s. Small makers produced specialized equipment using skilled craftsmen. Production numbers were measured in hundreds per month, not thousands per week. Quality was kept up through checking each item by hand and manual adjustment, not statistical process control or automated testing. Hermann's December 1943 report to the Reich Ministry of Armaments was called The American Radio Industry, a look at factory power and strategic meaning. It documented American electronics production in terrible detail. United States industry was making yearly what would take Germany 20 years to produce. The gap was not just technical, it was industrial, organizational, and philosophical. The report guessed that American factories could make enough military radios to equip 1,000 divisions, though the Americans only had about 90 divisions. The extra capacity meant that American forces had endless replacement equipment. Broken radios were not fixed in the field. They were replaced. Old models were retired and sent to training units. Newer, better designs were always being brought in, not as tests, but as mass-produced equipment spread across whole war zones. German forces, meanwhile, carefully protected every radio. Field technicians made repairs under combat conditions, taking parts from broken sets to keep others working. Replacement equipment arrived rarely, if at all. Newer designs stayed in limited production because changing the tools would slow down the making of existing models. The German Army used radios designed in the early 1930s alongside newer equipment, creating repair nightmares and training problems. The crystal supply situation was especially serious. By late 1943, German supply officers estimated they needed 5 million precise crystals for current radio equipment and planned upgrades. Domestic production capacity was about 200,000 crystals each year. Even if Germany spent huge money on making more crystals, it would take over a decade to make 5 million units. The Americans, based on SPY estimates, were making 30 million crystals yearly. They had solved the quartz supply problem by finding deposits in Brazil, mining operations in Arkansas, and even growing synthetic crystals in labs. American crystals were not just plentiful, they were better in quality, achieving frequency stabilities that German labs could barely measure, let alone make. The check of captured American test equipment revealed another part of the industrial gap. American radio factories used automatic test sets that measured frequency, power output, modulation quality, and sensitivity in seconds. These testers were themselves advanced electronic tools made in numbers that allowed every assembly line station to have dedicated test equipment. German factories used manual test steps, needing skilled technicians, and minutes per unit. One captured test set, a Measurements Corporation signal generator, became a prized possession of the technical testing facility. This single tool, standard equipment in American factories, could create exactly calibrated signals across the entire radio frequency range. It had cost about $300 to build. The equal German equipment needed a lab filled with separate oscillators, power reducers, and frequency meters, costing thousands of Reichmarks and needing constant tuning by engineers. By early 1944, the message from technical intelligence was clear and frightening. American communication superiority was complete, irreversible, and growing. Every month, American factories produced more radios than Germany had in its entire military stock. Every captured example showed small improvements, better designs, and factory skill that Germany could not match. The introduction of American radar systems in late 1943 and early 1944 drove home the message with even greater force. Radar was radio technology pushed to its highest point, using microwave frequencies, pulse techniques, and advanced signal processing. The Americans were mass-producing radar sets for ships, airplanes, and ground locations, with the same factory efficiency they applied to voice radios. A captured SCR-584 fire control radar checked in March 1944 showed technical abilities that German radar scientists had only dreamed about. The set worked on the extremely high frequency of 3,000 MHz, used a precise tracking mount with automatic following circuits, and achieved accuracy that allowed anti-aircraft guns to destroy enemy aircraft with terrible effectiveness. The SCR-584 weighed over 10,000 lbs and needed a dedicated vehicle for moving. Yet, American factories were making them by the hundreds. German radar development had focused on long-wave systems working below 1,000 MHz because German industry could not make the specialized vacuum tubes needed for higher frequencies. The magnetron tubes used in American microwave radar needed precise machine work, special materials, and factory methods that Germany did not have. Even when German scientists designed microwave radar systems on paper, they couldn't be built because the parts simply didn't exist in German industry. The careful check of captured American equipment continued through 1944 as Allied forces moved up the Italian land and got ready for the invasion of France. Each new example added to the huge evidence showing American technical superiority. Improved radios appeared often. The SCR-694, brought in mid-1944, gave FM tank communication with longer range and better reliability. The SCR-619 aircraft radio offered hundreds of crystal-controlled channels and near-instant frequency switching. Most importantly, American equipment reliability constantly got better. Early production SCR-300 radios had occasional problems with water getting in and battery contacts. Captured examples from late 1944 showed redesigned cases, better seals, and changed circuits that fixed these issues. The Americans were not just building equipment, they were always improving it, based on field use and putting what they learned into ongoing production. German equipment, in contrast, often got worse in quality. As the war went on, material shortages forced the use of poorer components. Skilled workers were moved into combat units, replaced by less experienced staff. Quality checking suffered as factories focused on quantity over reliability. Radios that should have lasted for years began failing after months of service. By the time of the Normandy invasion in June 1944, German technical intelligence had documented the full picture of American communications superiority. Allied forces landing in France carried more radios than the entire German army owned. Every Allied company had radio contact with battalion headquarters. Every Allied battalion could reach division command. Artillery spotters directed fire from dozens of kilometers away with perfect accuracy because their radios never lost contact. German commanders trying to coordinate defenses found their communications breaking down under Allied jamming, artillery fire, and the simple mess of battle. Radios that worked perfectly on test ranges failed in combat. Crystal parts drifted off frequency in the Norman summer heat, making contact between units impossible. Battery-powered sets ran down fast because replacement batteries were unavailable. The communication system that German rules assumed would exist simply stopped working under the stress of battle. The technical reports flowing back to Berlin became increasingly desperate in tone. Chief Engineer Hermann, now working with German operations staff, wrote in August 1944 that Germany had already lost the electronic war. American jamming equipment, direction-finding systems, and signal spy abilities allowed the Allies to find and target any German radio transmission within minutes. German codes were broken, frequencies were monitored, and troop movements were tracked through radio traffic analysis. The final breakdown came in late 1944 and early 1945 as Germany's industrial base fell apart under Allied bombing. Factories making radio equipment were key targets. Telefunken's Berlin facilities were destroyed in November 1944. Lorenz production plants in Stuttgart were bombed repeatedly. The Crystal Production Center in Sudetenland fell to Soviet forces in January 1945. By March 1945, German radio production had mostly stopped. Existing equipment continued to work, kept going by increasingly desperate field technicians who took parts from broken sets and made temporary fixes with whatever materials they could find. Replacement radios simply did not exist. When a headquarters radio failed, commanders lost contact with their units. When tank radios broke down, armored groups became isolated clusters of vehicles unable to work together. The Americans, meanwhile, kept improving their equipment even as victory neared. New radios brought in early 1945 offered better range, extra channels, and improved reliability. Production continued at full capacity, not because more radios were needed, but because the industrial machine could not easily be stopped. By May 1945, American depots were filled with excess radio equipment that would never be used in combat. The end came on May 8, 1945. Germany surrendered completely to Allied forces. Among the items recorded by occupation authorities were the technical spy reports from Tunisia, Sicily, and Italy. These papers, marked most secret by German authorities and hidden in salt mines and underground archives, gave Allied investigators a special look at their own equipment. American technical teams searching through German facilities in the summer of 1945 were surprised to find how thoroughly the Germans had checked captured American radios. The reports were correct, detailed, and done professionally. They correctly named American technical benefits and honestly judged Germany's inability to match American capabilities. One report, written by Chief Engineer Klaus Hermann in April 1945, as Soviet forces closed in on Berlin, served as his final word on the technical war. He wrote that Germany's defeat was certain from the moment German engineers opened the first captured American radio in Tunisia. The frequency crystals, automatic circuits, and modular design showed a factory approach that Germany could never match. The Americans had industrialized warfare itself, using mass production methods for every part of military equipment. Herman concluded that future wars would be won not by the side with better soldiers or superior plans, but by the side with greater factory power to produce high-technology equipment in huge numbers. Germany had excellent soldiers, good generals, and decent plans. What Germany lacked was a factory base able to match American production. This lack was clearest in something as simple as a radio crystal ground to precise standards by teenage girls in factories that produced millions of units every year. While German labs struggled to make thousands, the post-war fate of the German engineers who checked, captured American equipment reflected the realities of the New World Order. Klaus Hermann was hired by American officials in 1946 and spent 2 years writing down German radio technology for United States intelligence. He later worked as a consultant to American electronics companies, helping them understand and improve upon German ideas that were worth saving. Many of his colleagues followed similar paths. The movement of smart people from Germany to America, formalized in Operation Paperclip and similar programs, moved thousands of German scientists and engineers to the United States. They brought knowledge of German technology, but more importantly, they learned American factory methods, mass production techniques, and the organizational thinking that had made American victory inevitable. In 1952, Herman published a technical paper in the Institute of Radio Engineers Proceedings called Comparative Analysis of German and American Military Radio Design Philosophy, 1939 to 1945. The paper, based on his war experience checking captured American equipment, documented in academic language what he had reported to the German Army High Command almost a decade earlier. American radio design, he wrote, focused on ease of manufacture, simplicity of operation, and reliability under all conditions over complex technology or component efficiency. German design aimed for technical excellence, theoretical perfection, and component saving, believing that skilled operators would make up for equipment weaknesses. One way scaled to millions of units and global use, the other did not. The paper became required reading in engineering schools and military academies. It guided a generation of American engineers who designed equipment for the Cold War, the space race, and the computer revolution. The lessons learned from German engineers checking American equipment shaped American technical dominance for decades. By the 1980s, many surviving German engineers who had worked in technical intelligence during World War II gathered for reunions and history meetings. They shared memories, compared notes, and reflected on their experiences. Klaus Hermann, then in his 70s, gave presentations on his work, checking captured American radios in Tunisia and Italy. At a conference in Munich in 1986, he showed pictures of the first SCR Fyodor 8 his team had looked at in February 1943. The images showed young German engineers leaning over the open radio case, measuring circuits, writing down parts and struggling to understand what they were seeing. Herman told his audience that the moment they took out the first crystal holder and saw 10 precise parts installed in a standard tank radio, he knew Germany had already lost the war. The frequency crystal, a small quartz wafer cut to exact sizes, represented the meeting point of physics, engineering, and factory organization. It was not a complex device in principle. Any decent lab could make one, but to produce millions to a standard quality level with perfect interchangeability at a cost low enough for installation in every military radio required a factory system that Germany simply did not possess. That system, created in America between 1941 and 1945, did not disappear when the war ended. It grew and changed, producing transistors, integrated circuits, microprocessors, and finally the computers and communication systems that define the modern world. The same companies that had mass-produced radio crystals for Sherman tanks later produced semiconductors for space missions, microchips for personal computers, and the parts that allowed global telecommunications. The lessons learned from German engineers checking American equipment in Tunisia became part of the base of modern technology: design for manufacture, standardize components, train operators simply, build testing into the process, scale production to meet demand. These principles, visible in every part of American radio equipment in World War II, became the standard way of working for all high-tech industries. In 1995, on the 50th anniversary of the war's end, the Smithsonian Institution opened an exhibit called Communications and Victory: The Radio War in 1939 to 1945. Among the displays was an SCR 508 tank radio with a serial number matching the unit checked by Chief Engineer Hermann in Tunisia in February 1943. The radio had been found in German archives and returned to the United States as part of a cultural exchange program. Beside the radio, the exhibit showed parts of German technical spy reports translated into English, documenting the check process and findings. Visitors could read Hermann's notes about crystal quality, circuit design, and factory skill. They could see photographs of German engineers measuring parts, testing circuits, and writing down data. The exhibit made clear that German technical experts saw American superiority, reported it correctly to their leaders, and understood what it meant. The exhibit also displayed German radio equipment for comparison. A Fu G5 tank radio sat next to the American SCR 508, allowing a direct side-by-side look. The German radio was bigger, heavier, more difficult to run, and less capable in every way you could measure. It showed excellent engineering, limited by small factory capacity. The American radio showed decent engineering multiplied by endless factory resources. The curator's notes explained that the exhibit was not about praising American technology or criticizing German equipment. Both sides had smart engineers who designed good equipment given their limitations. The difference was not intelligence, training, or book smarts. The difference was industrial thinking and manufacturing capacity. Americans built systems that worked reliably when run by minimally trained users. Germans built systems that worked brilliantly when run by highly trained experts. One approach scaled to a global war, the other did not. The final display in the exhibit was a small glass case holding a single radio crystal recovered from the SCR 508 checked in Tunisia. The crystal, no bigger than a stamp, was precisely cut quartz in a sealed metal holder. The label explained that this crystal, one of 10 installed in a standard American tank radio, required about 40 hours of German skilled labor to copy. The Americans had produced over 100 million such crystals during the war, a number that would have required every German radio technician to work for 500 years. The exhibit brought in over 200,000 visitors during its year-long run. Many were veterans who had used the radio equipment shown. Some were engineers interested in technology history. A few were historians studying the factory side of warfare, all left with a deeper understanding of how factory power determines military outcomes. Klaus Hermann died in 1997 at age 84. His obituary in the Institute of Electrical and Electronics Engineers Spectrum magazine noted his contributions to radio technology, his work in military intelligence during World War II, and his post-war career helping American companies understand German ideas. The obituary also mentioned his lifelong belief that Germany's defeat was decided not on battlefields, but in factories, not by soldiers, but by production workers, not through planned failures, but through factory limitations. His papers, donated to the Deutsches Museum in Munich, included over 2,000 pages of technical reports, circuit diagrams, part lists, and major reviews written between 1943 and 1945. These documents gave historians deep insight into how German technical experts saw American equipment and what they reported to the German Army High Command. Perhaps the most heartfelt document in the collection was a personal letter Hermann wrote to his wife in April 1945 as Berlin fell to Soviet forces. He had sent his family to relatives in Bavaria months earlier and remained in Berlin doing final technical checks until told to leave. In the letter, he wrote that he was about to destroy all secret documents and equipment to prevent capture. He thought about the 3 years spent checking American equipment from the first SCR-508 in Tunisia to the latest radar sets captured in the Ardennes. Every example, he wrote, confirmed the same finding. America had not just better equipment, but a completely different way of war. They had industrialized everything, from radio crystals to whole armies, using the same mass production thinking that built cars and refrigerators. Germany, Hermann wrote, had tried to fight a factory war with craftsman methods. It wasn't that German technology was worse. In many areas, German book knowledge was better than American, but theory does not win wars. Production capacity wins wars. The side that can build more tanks, more aircraft, more radios, and more everything will eventually defeat any enemy, no matter how skilled or brave. He ended the letter with a guess. The next war, if it came, would be even more factory-driven than the last. Victory would go to the nation with the greatest manufacturing ability, the most advanced technology, and the power to produce precise parts in unlimited numbers. America had shown these capabilities between 1941 and 1945. Any future opponent would need to match or beat American industrial power, something Hermann believed was impossible for any single nation. History proved him right. The Cold War that followed World War II became a competition of factory capacity, technical innovation, and manufacturing capability. The Soviet Union, despite huge resources and a massive population, could not match American electronics production, computer technology, or automated factories. The gap that Hermann found in radio crystals in 1943 grew to include semiconductors, microprocessors, and integrated circuits. The story of German technicians checking captured American radio equipment is, in the end, a story about industrial warfare and the huge change in manufacturing that happened in America during World War II. It is about the change of warfare from an activity mainly decided by plans, training, and courage to one decided by factory capacity, technical skill, and manufacturing efficiency. The frequency crystals that so impressed Hermann and his colleagues were not magic. They were precise engineering, yes, but more importantly, they were precise engineering scaled to mass production. American industry had learned to make millions of units to identical standards, something that had never been done before on that scale. This power, developed for radio crystals, extended to every part of military equipment and eventually to every consumer product America made. The lessons learned by German engineers checking American equipment in Tunisia, Sicily, and Italy were hard, but clear. Better individual equipment means nothing if it cannot be produced in quantity. Advanced technology is useless if operators cannot reliably use it. Theoretical excellence is worthless if manufacturing cannot achieve it consistently. Industrial capacity properly managed and directed defeats everything else. These lessons, bought at the cost of Germany's defeat, became the base of modern manufacturing philosophy. Design for production, build in quality, train users effectively, support equipment properly, scale to demand. The principles visible in American radio equipment in World War II now run global manufacturing in every industry. In the end, the story that began with Chief Engineer Klaus Hermann opening a captured radio case in Tunisia in February 1943 ended with the complete change of how nations prepare for and conduct war. The radio crystal, that small piece of precise engineered quartz, became a symbol of the Industrial Revolution in military matters. It represented the moment when victory stopped being determined mainly by battlefield skill and started being determined by factory output. The German engineers who checked American equipment understood this change as it happened. Their reports documented not just technical specifications, but the end of one kind of war and the beginning of another. They witnessed, analyzed, and reported the future of conflict. That their warnings were not listened to in Berlin did not lessen how accurate their judgments were. Today, the principles they named, mass production of precise components, factory automation, standardization for swapping parts, and design for manufacturability, are fundamental to every high-technology industry. The direct link runs from radio crystals ground in American factories in 1943 to microprocessors produced in Asian factories in the 21st century. The industrial thinking remains the same, only the scale has changed. The German technicians who tested captured American radio equipment in 1943 were not just checking communication devices. They were witnessing the future of warfare, technology, and factory organization. Their detailed reports, kept secret and filed away during the war, eventually became historical documents that explained not just why Germany lost, but how factory capacity determines the outcome of modern conflicts. Their finding, written in technical language, but clear in meaning, was that Germany had challenged the world's greatest industrial power with too little manufacturing capacity. The radio crystal, a precisely ground quartz oscillator produced by teenage American girls in numbers Germany could never match, told the whole story. Industrial warfare demands industrial capacity. Without it, no amount of battle skill, technological innovation, or personal courage can achieve victory. That lesson, learned by German engineers checking American radio equipment in underground labs across occupied Europe, remains important today. In an age of microelectronics, satellite communications, and computer-controlled warfare, the fundamental truth remains unchanged. The side with greater industrial capacity to produce high-technology equipment in overwhelming quantities will ultimately win. The Americans proved that principle between 1941 and 1945. The world has been adapting to its implications ever since.